Recording in progress.
So this is homework one, part E. We're going to be deriving the thermal resistance for the overall thermal resistance for series and parallel. So we'll start with the series, right? So let's assume we have a couple of different walls here. We have coffee on this side at TC. This middle section here is glass, right? That's our cup. This surface is T2. This surface will be T3. Here we have our insulator, um, right? Um, Here we have T4, and here we have our air at TA. So the length of our glass will be LG, the length of our insulation will be LI, right? So with this, we know a couple of things, right? So we have our net heat here, um, which equals um, our different um, rules here, right? So we know we have convection in this section. We have conduction here, and convection through here, right? So if we start on this side here, right, uh, we have our Q coffee, which equals our Q glass, which is our Q insulation, which is our Q air, right? And we can rewrite these individual Qs based on our different equations, right? So for convection, we know that the heat of convection is HA times our change in temperature, right? So we'll write that as T coffee minus T2, right? That's T2 up here. And then our glass is conduction, which we use Fourier's law for, right? So it's minus Ka times T2 minus T3, our change in temperature, over the length of our glass, our change in length. And it's the same thing for our insulation, just changing the location of the temperatures, right? So we have Ka, and now we have T3 minus T4, and then over the length of our insulation. And then for the air, we're back to convection. So we have HA times T4 minus the temperature of the air, right? So this is our Q net. And when we look individually at our Q for conduction and our Q for convection, right? We have Q conduction equals minus Ka delta T over change in length. And then our convection equals minus, or not minus. We have HA, right? Our thermal conductivity times our area times the delta T. Now we want to relate this, both of these, to our Ohm's law, right? Which is our change in velocity equals our current times our resistance. So when we look at this equation here, right, we have our change value, right? So if we come down to convection here, our change value is our temperature. So if we put that on one side, we have delta T equals Q convection times 1 over HA. And when we're looking at our Ohm's law here, right, so this is velocity, the change in velocity rather, and this is our current, right? This is what is moving through our system, right? And so what is moving through our system here, we have our Q, right? So when we're relating these equations, delta, our change in velocity is our change in temperature, and our I is our change in, or our heat, right? So our current relates to our Q convection. That leaves R being 1 over HA. So our thermal resistance for convection is 1 over HA, right? And so when we go back up to conduction here, we know that our I is going to be the same, right? We have our Q conduction as our I. We know that our change of velocity is going to be our delta V. So if we bring this down here, we set it equal to delta T again, right? That's our delta V equals our Q conduction times our change in length over our negative Ka, right? So our thermal resistance for conduction is our delta L over negative Ka, right? And so if we're looking at our total, right, here it would be our total temperature change, right? And then I is Q, like we established in both of these equations. So this is our Q net. And then we'll have our R total. So when we're looking back at our Q net, or not at our Q net, at our thermal resistances, we know that we have a convection, a conduction, a conduction, and a convection, right? So our R total will be, sorry, move this over. Right, our convection, which is 1 over, the first one was coffee. So it's the thermal, our HC times our area of our C. And then it is it's our, right, so our total is just the sum of our individual R's. So it's the our R of a coffee, right? So HC times our area of our coffee plus R, what was next? Right, so our glass, so it's L glass over minus K glass times our A glass, right? And then we move on to insulation. So it's Li over minus Ki Ai plus 1 over H air, area, air, right? So our overall thermal resistance right, for series is this up here, right? So we have our individual process or our individual sections. We take the sum of their individual thermal resistances, and whether it's for convection or conduction, we know based on, or we can figure out based on our picture, right? And so you'll do that individually for each section, right? So we have our convection, our conduction, and then our convection, right? We know convection is 1 over HA, so we take 1 over HA for the coffee. We know conduction's L over minus Ka. We do that for the glass and the insulation. And then once again, convection for the air. So we know that it's 1 over the H air times our area of our air, or our cross-sectional area, right? So this is our total thermal resistance for surfaces in series. If we look at surfaces in parallel, right? So let's say we have air, then we have, let's say this is a wall here. We have our glass, and let's still use insulation. Then we have a room on this side, right? So we just related it to delta V equals IR. Now in parallel, R is a little different. So we knew that R total last time, right? For series, R total is our sum of our totals. But for in parallel, R total is 1 over R total, right? So we would have 1 over R1, 1 over R2, and so on and so forth. And that is our new R total, right? It's our inverse. So if we look at Q net, right? For this, it would be the Q over glass plus the Q over insulation. And when we look at this, we can break down the Qs, right? So we have our Q glass. We know this is by conduction, right? Going into, our conduction through our glass, right? So we have our minus Ka, our delta T over L glass, right? And then we can do the same thing for the insulation. Qi equals minus Ka delta T Li, right? And so if we remember from in series, we know that this Q value, this is our I. The T value, this is our delta V. So what we're left with is our minus Ka our minus or our L over Ka, right? For the individual, depending on which one it is, right? And so, as I explained in the beginning, right? So, in parallel, it is no longer, just the sum of our totals. It's the sum of 1 over our total. So, if we look at this system here, we have 1 over our total equals, right? So R for our Q glass, right? This is length of the glass over minus Ka, and this is length of the insulation over minus Ka, right? So if we take that inverse, we then get minus Ka over length of the glass plus minus Ka over length of the insulation, right? And so this is our overall thermal resistance overall. For surfaces in parallel. Right. So the next part of this, we're going to look at what happens when you combine them. Right. So if we look at the normal structure of, let's say, like a wall of a house, right? Right. And so this is our structure, right? So we have our room over here. We have our stud, right? Technically, there'd be drywall, but we're going to just say there's a stud. We have our insulation. And then we have like our outside material, which is something like brick, right? And then on this side, let's say we have a double paned window, right? So we have our glass, the little bit of air or argon, but we're going to say air, and then glass again, right? So, and then out here we have our outside, right? So what we're going to do here, we are going to break this down a little bit. we're going to break it down into our two different sections, right? We have our window and we have our non-window, right? So if we look at the QNet for our wall area, right? We have our room, our heat of our room, which is convection, right? We then have the stud, which is conduction. Then it is our insulation, which is conduction. Then our brick, which is also conduction. And then finally, we end with our air, or our outside. So I'm just going to label that as Q out. And that is also convection, right? So when we look at this, right? So this is the same setup that we had when we went through this example, right? We have our QNet. Our QNet equals our coffee, glass, insulation, air. This is the same thing, right? So this is for our total, just the R total of a series. And let's say this is the inside, right? So if you were to break this down, right, we have our 1 over HA, our L over KA, so on and so forth, right? And that is all broken down into this R total of a series. And then we can look at our second section here, right? We have our glass, our air, and our glass, and of course our room and our outside, right? We break this one down exactly the same way as we did the first part, right? So we have our Q room, which is convection. Then our glass 1, which is conduction. Then we go to another, we go to an air, which is convection. Then we go to our glass 2, which is conduction. And then finally, we have our Q outside, which is convection, right? So this one's a little bit different because we have 3 convections rather than 2, but it is still our 1 over HA, our L over minus KA, 1 over HA, and then L over KA, 1 over HA, right? So that all makes up our R total, our R total in this series, and we'll refer to this as window or as win, right? Now we want to look at our total thermal resistance, right? And when we look at this, we have to look at our parallel now, right? We are parallel here. So if you come back up here to this section of parallel, our total is it's our 1 over our total, right? So we take that value, right? We know this is for parallel. And so it is our 1 over our first set that we broke it into. So it's our total for the series. What did I label it? Inside. Plus, right, our 1 over, and this is our second one here, our R total for this series of the window, right? And so our overall thermal resistance for a series and parallel, right? So, for example, like just a normal wall window setup, right? We have our the sum of our inverse series R totals, right? And so that kind of breaks down what the overall thermal resistances are for series surfaces in series, surfaces in parallel, and then we kind of looked at this example when they're both in series and parallel, right? And we know that that's just like a wall with a window. So that is everything for homework 1 part E. Thank you.